Operating systems are the foundation of modern computing. They provide the foundation on which application programs run, while ensuring efficient utilization of the computer's hardware resources. Let's explore some basic concepts and functionalities of the operating system. But before we start, we must first discuss the computer system components to understand the relationship of the users and computers and everything in between. First, the users in this system are the people that utilizes the computer and uses its application programs. Then, the application programs, which is also known as software, define ways in which the system resources are used to solve the computing problems of the users. Next is the operating system. This is the component that controls and coordinates use of the hardware among various application users. Then, for the last is hardware, which provides basic computing resources such as CPU, memory, I/O devices, storage, and network resources. In this context, the OS is a critical program that serves as a bridge or an intermediary between the user and the computer's hardware. It plays a dual role, allocating resources like memory and CPU time, and controlling the execution of various programs. There are various types of operating systems, each tailored to specific needs and environments. Let's explore some of the most common types and their key features. The first one is called Single User, Single Tasking OS. It is an operating system which you are only able to do one thing at a time. For example, a user can only print a document or download images one at a time. Next is the Single User Multitasking OS. It is the most used operating system today since a single user can do many things at a time. For example, a user can write an article using a word processor while also browsing the internet or checking their social media applications. The third one is Multi-User OS. In this OS, multiple users can access the system simultaneously. For example, on a server that utilizes Multi-User OS, a user can edit a document while another one is running a program, both utilizing shared system resources without problems or any interference. The fourth one is Multitasking OS. This operating system allows several programs to run at the same time. For example, on a Windows PC, a user can browse the internet, listen to music, and download files simultaneously. The fifth one is the Real-Time OS or the RTOS. This operating system is designed for immediate responses. For example, in an industrial automation system, the RTOS ensures that a robotic arm receives and executes commands in real time to maintain precision and safety. Next is the Mobile OS. This operating system are mostly used by smartphones and other handheld devices. It allows users to make calls, send messages, and use apps through an intuitive touchscreen interface. The last one is the Distributed OS. This operating system manages a network of computers to function as a single system. For example, in cloud computing, a distributed OS ensures seamless sharing of resources like storage and processing power across multiple servers. Operating systems are known to perform these key responsibilities. First is the process management, where the operating system creates, schedules, and terminates processes ensuring that they run without any conflicts. It also synchronizes processes to maintain data consistency. Next is memory management. This involves efficient memory allocation to programs and ensuring that no process can access unauthorized memory spaces. The third function is file management, where operating systems provide a file system for users to store and organize data securely. Next is input-output management. By managing device interactions and data transfers, the operating system can ensure smooth operation between hardware components. And lastly, security and protection. From verifying user identities to restricting resource access, the operating system safeguards the system from unauthorized use.
CPU scheduling is the process of determining the order of the execution of processes in the CPU. It has different methods that will be tackled later on, but let's first know more about CPU scheduling. Let's talk about the process execution cycle. Turnaround time is the total time it takes for a process to be completed after it is executed. The formula for the turnaround time is the difference between completion time and the arrival time of the process. Arrival time, as the word said, is the time the process arrives in the queue. Next is waiting time. It is the total time a process spends waiting in the queue. Its formula is the difference between turnaround time and burst time. Burst time is the total time it took for the process to be completed after it runs. Lastly is response time. It is the time it took for the process waiting after it arrives in the queue and before it starts executing for the first time. It's different from the waiting time in a sense that it don't account the waiting time when it gets preempted by another process without completing just yet. Now, there are two basic concepts of CPU scheduling: context switching and time quantum. Context switching is the process of saving the state of a process and loading the state of the next process. This makes for an efficient CPU scheduling. For example, let's say you're running a process that has burst time of 8 seconds and you run it for 5 seconds before saving it and loading the next scheduled process. The next time you go back to the process again, this time you'll just gonna need to run it for 3 seconds for it to be completed. Next is time quantum. Time quantum is allocated time for the process to run before being preempted. Now, we will tackle the modes of CPU scheduling: preemptive and non-preemptive. Preemptive scheduling is where the OS can interrupt a running process to run another process. This is where time quantum can be used, where it sets a running time for each process before it gets preempted by another, whether it is finished or not. Non-preemptive scheduling, on the other hand, is much simpler because it lets the process currently run until completion before it loads and run another process. First come, first server. Processes are executed to completion in order they arrive in ready queue. Always non-preemptive. Shortest job first, or SJF. Non-preemptive CPU scheduling algorithm where the process with the smallest burst time is executed first. Shortest remaining time first, or SRTF. Preemptive CPU scheduling algorithm where the process with the shortest remaining burst time is executed next. Round-robin scheduling, or RR. CPU scheduling algorithm that allocates CPU to each process for a fixed time quantum, also called a time slice. After each time quantum, the process is interrupted and the next process in the ready queue is given a chance to execute. This continues in a circular manner, ensuring that each process gets a fair share of CPU time. Shortest remaining time first. Explanation. At time 0, only P1 has arrived. CPU executes P1. At time 1, P2 arrives with a burst time of 4. Since P2's burst time is shorter than P1's remaining time 7, CPU switches to P2. P3 arrives with a burst time of 2, which is shorter than P2's remaining time 3. CPU switches to P3. At time 3, P4 arrives with a burst time of 1, which is the shortest. CPU switches to P4. After time 4, P4 completes. CPU resumes P3, followed by P2, finally P1. Disk scheduling. A technique operating system used to manage the order in which disk I/O requests are processed. This scheduling is also known as I/O scheduling.
And for the last topic assigned to our group, let's move on to disk scheduling. Disk scheduling is a technique in operating systems used to manage the order in which disk input-output requests are processed. Disk scheduling is also known as input-output scheduling. Let's move on to these concepts. First, tracks. Tracks are the concentric circles etched onto the surface of a disk where data is stored. Each track serves as a pathway for data retrieval and storage. Sectors. Each track is further divided into smaller units called sectors. This subdivision allows for more efficient data management and retrieval. Cylinders. It's defined as a set of tracks that are aligned vertically across multiple platters of a disk. When the read-write head is positioned over a cylinder, it can access the same track number on different platters simultaneously, enhancing data retrieval efficiency. Next is disk access time. It is the total time it takes for the disk to locate and retrieve the requested data. Transfer time. Once the head is positioned over the correct track, rotational latency is the waiting time for the desired sector to rotate into position beneath the read-write head. This time can be influenced by the speed of the disk's rotation. Next is seek time. This is the duration required for the disk read-write head to move to the appropriate track where data is stored. Seek time can vary significantly based on the initial position of the head and the target track. And lastly, rotational latency. After the head has located the correct sector, transfer time is the duration it takes to read or write the actual data. This time is dependent on the data transfer rate of the disk. Moving on to the disk scheduling algorithm. First is FCFS, also known as first come, first serve. It is the most basic disk scheduling algorithm available. Requests are handled in FCFS according to the order which they enter the disk queue. Meaning, the disk queue will determine the next sequence or the sequence in which the head will go through. Next is SSTF, which is shortest seek time first. The requests that take the least amount of time to find are processed first. So each request's seek time in the queue is determined in advance, and it is then scheduled based on that calculation. The request close to the disk arm will therefore be processed first, since SSTF improves system throughput and lowers average response time. It is unquestionably superior to FCFS. Next is scan. The disk arm reverses its direction and then scans the previously scanned path another. So there can be a large number of pending requests at the other end, or there might be none at all at the scanned area. Next is C-scan. Circular, or also known as circular scan, is a modification of the scan algorithm. In this approach, when the disk head reaches the one end, it does not reverse its direction. Instead, it jumps to the opposite end and resumes scanning in the same direction. Next is look, which is the only distinction between this and the scan disk scheduling algorithm is that despite reaching the end of the disk arm only reaches the final service request in front of the head before turning around. Next is CLOOK. This resembles the CS scan, this scheduling algorithm, just as look is comparable to the scan algorithm. Even though it reaches the end, the disk arm in CLOOK only serves the final request in front of the head before moving on to the final request at the other end. As a result, it also avoids the additional time brought on by unnecessary disk travel.